Okay, welcome in. This video we're going to talk about personally one of my favorite functions. I think it's extremely powerful, extremely useful, very fast, a lot of wide-ranging applications. That is the aggregate function. And as you can guess, it does a lot of aggregating of data within R, but it's pretty cool and hopefully you will agree with me that it's pretty useful. So we're going to be looking at the iris data, which we've looked at before. Really nice because a lot of people will just like load in data sets from their computer and you can't really see what it is. But the nice thing about iris is that it's just defined in R. So I didn't load anything. You just type iris. In this case, I'm looking at the head of iris, the top 6 rows, and you'll have it in your R loaded already. So it's got a bunch of information about flowers, the length and width of the sepal, which I guess is a part of the flower, the length and width of the petal, the species, and I actually, this is a little bit of a spoiler, so I'm going to remove that because I was just preparing this video before. So bear with me, head iris. Okay, and we have the species here as well. I just removed a column that we're going to be talking about later. So let's say that you wanted to get, you have all these different species, and in this case, we're just looking at the head, so we can just see there's a Setosa, but we also have Virginica, and in general, we can see how many species we have by using the unique function and looking at this iris species vector. We have Setosa, versicolor, and Virginica. And let's say we want to figure out which flower has the largest petal width on average. And you could do something like mean of iris petal width, where iris species equals Setosa, and you could get this, 0.246. I'm going to save this here for later so that we can check it. You could do this, but then you'd have to do a Virginica, you'd have to do a versicolor. If you had a lot more species, it would be even more work. You could do some sort of for loop, but that seems like a lot of work. Instead, we can just very nicely use the aggregate function. So I've got the aggregate function over here. The first argument that we pass in is iris, so that's just the data. Actually, sorry, the first argument we pass in is the vector or the data or whatever that we want to aggregate. In this case, it's going to be petal width. And then the next, do I want petal width? Yeah, petal width. The next argument that we're going to pass in is what we aggregate by. So we're going to say by equals, for some reason, we need to pass in something that is a list. So we just do list. And you'll actually see that it's not for some reason. There's a real reason why. In this case, we want to aggregate by species. We want to see the average of the petal width by species. So we do iris $ species. So we want to aggregate the petal width by the species. And finally, what's the way we want to aggregate this? Well, we want, I think it's fun. Let me just make sure. This is on the fly, a nice way to like double check your functions is just to type question mark aggregate, and then you can see all this useful information about the function. Specifically, you can see the arguments, an R object, by, which is a list of grouping elements, and then fun, which is what I was looking for. I wanted to see if it was all caps or not. So fun is going to be the function that we actually want to apply over our petal widths by species. And in this case, we just want that function to be mean, which is very nice and simple. If I wanted to get a little more fancy, I could say I want to pass in some function x such that, and this is a lot of extra work, but sometimes it's useful, such that we take the mean of x and we remove NAs. And if you haven't seen this looks like a little bit weird, but it's very useful and very simple. This is just saying NA remove. Do you want to take out the values that are NA? And I'm saying true. Yes, I do want to take out the values that are NA. So like if you wanted to take the mean of 1, 2, NA3, you would get NA because the one NA will ruin the party for everybody. You're taking the mean of 1, 2, 3 and NA is in there. So you're going to get NA back. However, you say remove NAs, NA remove is true. It's just going to take out NA and calculate the mean of the rest of the vector 1, 2, 3. So that's what's nice here. And we've already talked about how to define functions. In this case, the function has one input x, you're returning the mean of x and removing any NA. So that can be useful. And you could predefine this function beforehand, so you didn't have to type it directly into aggregate, but this is how I usually do it. But let's just do the mean for now, so we don't get too crazy, because nothing in iris is NA. And I'm going to hit return, and boom, I have by group one. That's the first thing we're grouping by species of the different irises, and then I have my actual output, which is the mean of the petal width. And immediately we can see that Setosa is the smallest, versicolor next smallest, Virginica is the largest. And we can also check by our manual way of doing it. We got 0.246 for our mean of the petal width for Setosa, and that matches here. So we are happy. And the other nice thing about Aggregate is that you can stack a bunch of, or you can group by a bunch of different columns. So let's say I wanted to see if, in addition to species, I wanted to kind of aggregate by petal length as well. So I want to look at petal length. However, these values go down to 1 decimal. So like, there's not a lot of different, there's not a lot of values maybe in the 1.4 bucket. So what I'm going to do is I'm going to redefine, I'm going to say length round. So this is how I define a new column. And that's just going to be the rounded value of iris petal length. So rounding to the nearest integer instead of like a decimal number. And now if I look at iris length round, there's more buckets. And this might be a little bit weird, but imagine if I did iris petal length, the unique iris petal length, if I saw how many different values are in that, and that there's going to be a lot. There's 43 different unique values in a data table with 150 rows. So there's really only like 4 values per bucket. 4 times 41 is close to 150. Whereas if I do length round, if I look at the unique values of that, there's only 7 buckets. So there's way more values per bucket. So it all depends on what you want. In this case, I just want to have more values per bucket. If I look at a table of this value, I have 24 petals, in the bucket of 1, 26 petals in the bucket of 2, etc. So that's a little aside. It all depends on kind of what you want, but in this case, I want to have kind of larger buckets, and we can copy and paste our aggregate function. And the only thing we're going to add is, remember, we're aggregating over petal width by species. We also want to aggregate by the rounded length. So we aggregate first by species, then by rounded length, and we are also taking the mean. And if we run it, we are going to get this. And in this case, the first column is the first group we group by, second column is the second group we group by, third column is the average petal width. So for example, a versicolor with a petal length of 3 rounded to the nearest integer is going to have this width. One thing that's annoying is that you can see, for some reason, R sorts by the second column. So in the first column, you'll get some versicolor, Virginica, versicolor, Virginica. In the second column, it's straight counting from, a not strictly increasing, but increasing. So if you want, you could just resort this by this first column. But you can see that there's a positive kind of relationship. Like if you look at Virginica, for example, we don't change the species, but we change the rounded petal length. And that's the petal width is going to increase. So for a petal length of 5, you get this 1.96. For a petal length of 6, it goes up to 2.07 for the petal width. Petal length of 7, it goes up to 2.15. So kind of a nice way to see that increasing relationship. And we don't have to like just look at the mean. We could just as easily do the standard deviation, standard deviation of these different values. And this just gives us some like variance measure. And a really quick question, I guess this will be our last question before we end the video. Why do we have an NA value for Virginica 4? Virginica, where the rounded petal length is 4. So just take a second and see if you can answer that. Well, you can pause the video. So the reason why is because if we look at iris, where species equals Virginica, and length round equals 4. That's not what I want. Iris. I have to specify iris $, iris $. I forgot this is in the data table. There are actually 0 rows where the Virginica species has 0 rows. It doesn't have any irises where the length the rounded length is 4. And if I just want to look at the Virginicas, let's do that. That's not right. Never mind. I might have messed something up. Iris. Yeah, let's just look at this. Sorry. Yeah, okay. Okay, so sorry about that. I just forgot some syntax for a second. Let's just look at our original data. We have all our Virginicas here. And here's this last column is our rounded length column. We see 1 4 here, but then we don't see any other 4s in the data. And we can't take the standard deviation of a constant. R doesn't like it. If I just try to take the standard deviation of a single number, R will spit out NA, which is why we got NA when we ran this value. So it's just because there's 1 or 0 values for that bucket. And that's kind of a reason why you want to have larger buckets so you don't get weird results for this. But anyways, hopefully you enjoy the aggregate function as well. I think this list thing can be a little bit tricky, but it's useful. Remember, you can specify your function to be as complicated as you want. And it's just a very fast, very quick way for big data sets to get sort of cool aggregates instead of doing something very manual like this or running a for loop. So hopefully you like that, and we will see you next time.